Welcome back. If you're following in the manual, we're on page 90. We're talking about methods of stabilization. If you will look in your manual from pages 90 to 102, what we've tried to do there is sort of develop not exactly a cookbook approach, but you can look in there and see a particular type of slide, as we talked about our putting categories earlier this morning, and it will give you reference to the section that might be appropriate or the type of repair method. Before I get into the stabilization methods, I'd like to have a foreword or just a few comments. I want to emphasize in this course that large slide repair methods versus small slide repair methods are essentially the same. A lot of the data that we have and a lot of the slides and photographs we have, a lot of them are large slides that we'll show in this course, but I'd like to emphasize that there's a lot more data available for the large slides. But I want to emphasize also that the concepts are essentially the same. Whether maintenance will be directly or indirectly involved will be a matter of possibly of the size of the slide and so on. Maintenance people or supervisors, they do need a working knowledge of the methods that I'm going to be talking about, whether you can do the job yourself. You may have to let the particular landslide to a contract. You may have to make a decision whether to call a geotechnical engineer. Geotechnical engineers are ones that are trained in landslide mechanics. They are trained to do stability analysis. And also, you need this knowledge for inspection purposes. So what we've done in the stabilization methods is try to provide a framework or an overview of the methods. Some methods may not be applicable to other parts of the country, but we want to look at all these methods. So let's start. There's going to be 3 sections to this section 5. We're going to talk about basic approaches. In other words, what methods can we use to repair a landslide? We're going to talk about repair methods, which will be the major portion of this discussion. And then we'll talk about repair economics. Most of our time in this section will be spent on repair methods. Let's just briefly look at basic approaches, and there's more discussion in the manual on this, more in depth, but there's essentially about 5 approaches that we can use to repair a landslide. We can modify the slope profile in some manner, either to increase the resistant forces or maybe unload the top of it to lighten up the load at the top of the slope. And as we talked earlier, we can control the drainage and seepage. And a third method is construct stabilizing structures. And the 4th and 5th approaches are removal or replacement and relocate it and avoid the problem. But let's go right into the first method there. There's several techniques of modifying the slope, but let me make one comment back up here a minute and stress one important principle here. If we lower water in a field, we increase the strength. If we raise it, the strength decreases. So this is an extremely important point of view for controlling subsurface and surface waters. And we've talked about surface waters earlier. Let's look at what kind of techniques we can use for modifying the slope profile. Well, there's several things we can do. We can flatten the slope. We can use soil and rock berms at the toe of the slope. We can use shear trenches, and we'll get into the discussion on this. We can bench the slope, and also we can use excavation. Let's look at how we would flatten the slope. First, I'd like to say that flattening the slope, and I like to emphasize this is a primary corrective measure for small slides as well as large slides. There's certain distinctive advantages when we use this technique. One that we call minimum disturbance to the highway. In other words, If we do have a landslide, usually we can route traffic through. If it's a failure in the embankment, depends on whether it wipes both lanes out, or usually a slide will leave some room there. There's usually some room for traffic to move through. Sometimes if it's a cut slope, we can usually manage, or maintenance does a good job, I think, of managing to keep the road open. An appropriate place to apply the technique of flattening the slope is a deep rotational type failure. Look at it in cross-sectional view. Basically, the concept here of what we're trying to do, originally the slope may be a 2 to 1, or it could have been 1.5 to 1, and we're simply flattening the slope out to, say, a 3 to 1 or a 4 to 1. An ideal type example where a slope flattening might apply is shown in this landslide. Notice that there's a scarp at the top and a bulge at the bottom. We could excavate this, remove the material, and flatten this slope out. This slope here is probably a 2 to 1 slope. We could probably make it 3 to 1 or 4 to 1, and that's a simple solution. It's very easy, and it's one of the cheapest because we can use some of the material we take out and put it back in. Another place where we can apply slope flattening, we have a toe slump in a field. It may start out as just a small rotational failure, but the danger in a slide like this, especially if it's a very steep slope, which you find on interstates, but you also find real tall fields in county roads and other type of roads, state roads. But always observe that toe slump because it can eat back up. In other words, it fails at the bottom, then another failure occurs, and then another one, and soon you've got a problem in the traffic lanes. So simple slope flattening there could correct this situation before it develops into a major problem. And here again, we talked about waste material from rock falls and so on. This is where the inventory system would come in to be really effective. We could store these materials close to areas where we're having problems. An example of how we would flatten the slope in this 3D drawing here, we would simply bring in maybe waste material, or we may have to haul some material in. In a slide like this is a very large slide. If you look in the monitor there, the number there, 35, that's the man standing there. He's standing on top of the slope there. This is not a type of slide that probably maintenance would get involved, but it's important that they recognize that something is developing there. There's a small scarp there at the top. Something will eventually have to be done. And slope flattening applied to this type of particular situation, well, eventually, if you get up around 30 feet or more, you may have to go to another technique. So the method's usually quite effective up to about 30 feet. That's just another view of that same slide, the toe there. Slope flattening also is an effective technique for over-steepened slopes near the toe. Perhaps the steepness there has been caused by erosion, or maybe it was constructed that way. But here again, simply flatten the slope out. What are the steps involved in flattening the slope? Well, first thing is to obtain a cross-section of the slope. And then the second question you have to answer is, what slope do I use? What flattened slope would I choose? Normally you can use about a 3 to 4, 3 horizontal to 1 vertical, or 4 horizontal to 1 vertical. Usually will do the job. However, when you're using a flattened slope, you have to be very cautious. This is one reason, as shown in this sketch here. We've placed all the flattened slope on the left side, or the driving side of this circular rotational failure, and it's not going to do us much good in this case. And it could be that if the failure is very deep, cuts down into the foundation materials, the toe comes up way beyond. In this case, the flattened slope would do us no good because we're just adding more force to the driving side, and the slide would simply rotate. The thing we need to do is to be sure we can cover the toe of the bulge. Okay, obtain borrow material. One of the things we want to look for in obtaining the borrow material, always look on site. Usually you can find a borrow area that's very close. You can reuse some of the material that you take out, which is the next step. We either completely or partially remove some of the failed material. But we've got to be cautious when we start excavating, and what we're trying to do is remove down to the failure plane. But we've got to be very cautious when we do this. Generally excavate it in 50 to 100-foot sections, and then you want to backfill to the new flattened slope immediately. In other words, you build it in segments. For excavation purposes, just some guidelines. If you start out with a 2-to-1 slope, you can go to 1-to-1, 3-to-1, 2-to-1. If the slope is originally 4-to-1, you might excavate down to 3-to-1. When you remove the material, if the soil is very wet, you need to dry it out. One possibility there is dry it to the plastic limit, or alternately, this diagram shows up much better in the book, but you can, this plastic limit versus the liquid limit, you can obtain the optimum moisture content from this graph, which is the water content that you want to dry the material to. There's more details in the manual on that. Another just rule of the thumb, I guess, is dry it out, and if it's ready to plow, it's probably okay. Okay, when we do a flattened slope, we want to place a drainage blanket against the excavated slope. A drainage blanket is used for controlling subsurface or internal water. Generally, it's constructed of non-degradable type stone or just good, clean stone. If you have a question about what type of stone or whatever to use, talk to a geotechnical engineer or call someone in the state, Division of Materials, or whatever the location, wherever the geotechnical engineer may be located in the state. Again, you want to put it on the lower portion of the distressed slope, and it's good practice to put in a drainage pipe in the drainage blanket. This helps remove the water very quickly. Why do we want to do this? Well, as you see here, we place the drainage blanket against the slope. If the slope is composed of clays or silts, and also if the fill material is composed of clays or silts, what you want to do is wrap that with a geotextile filter fabric. The reason for that is, if you place the clean stone against the soil or clay or silt, the fine particles from the clay or fill are going to just enter the stone and clog it up. And then it defeats the whole purpose of the reason to put it there. But what we're trying to do is keep the water table from entering the new flattened slope. Just another situation to illustrate this, we get seepage not only from the subsurface or groundwater. You'll notice in the monitor there, WT, that's the water table, but also just from rainfall and snow melt, we get water entering from the surface down into the new flattened slope. So what we're trying to do is keep the water completely out of the new addition. And remember, if the water table comes up from whatever source of water is, we lower the strength of the new correction. So the key point here is to keep the water table, keep the thing drained at all times. Another scheme that could be used on small repairs, we've done, what this slide really shows is that we've excavated the slide out, the slide material, and we can use a backhoe to construct trenches back into the excavated slope. Let me show this in another cross-section here. This is just a way of reaching back into the slide and taking that water table and moving it back to the right of the screen there. In other words, keeping it, it's another method of keeping the water table from entering the new material or the flattened slope. An example here in this slide of a drainage blanket being installed. You note there on the monitor that the material's been excavated and they're putting in a drainage blanket. Just another illustration of another example where a drainage blanket might be constructed before the slope's flattened or whatever. Notice they're putting a geotextile down on the clay soil there and then installing the stone. Another view of that, closer view. The final steps in constructing a flattened slope, we place the flattened slope against the drainage blanket then and the distress slope, and of course we would reseed it. And you should do the third thing, inspect it periodically after the correction's been made. Don't assume that it's going to be the final say-so, but you should go back and look at that to be sure that you've corrected the landslide. The final step, here's an example where they've flattened the slope out. This is a very cheap method. It's one that should be one of the first things to consider when you're looking at this landslide. In this particular slide here, they're flattening the cut slope there on the right of your monitor. And that's in a cut slope there where they're flattening, and they can solve a good problem there by flattening it back. I think originally they were getting sloughs in the cut slope material there. Another example where another type of slide where a cut slope, a slope flattening might work, is shown here. Note the vertical cracks at the top. It's somewhat of a rotational type failure. This is a very typical type failure you see along a lot of highways. Here they've used a slope flattening and they've put sort of a berm there. I don't know, they've used stone, I think, for the correction. Now, like I was saying, when you get up around, I'll say 30 feet in height of the landslide, sometimes it's good to go to a combination of slope flattening and berms. Berms are used as a counterweight with slides that have failed near the toe. Generally, we need about, roughly a fourth to a half failure mass to correct the slide. Let's look at this more in detail, a little bit more. The principle here, if you note the slide is rotational in this particular graph, what we're doing is adding weight to the right side there or building a berm. We're trying to balance the weight of the slide. So, and also note that we're covering the toe of the slide. So for a deep failure, we could maybe use slope flattening, but also build the material on out to the right there and cover the toe of the slide. We've got to be cautious when we build a berm. We want to make sure that we don't increase the driving forces. In other words, the forces on that graph are on the left side. We want to be sure, as I mentioned, extend the berm beyond the toe of the failure. And the steps in constructing a berm, maybe possibly with slope flattening, is very similar to what I just described for slope flattening. Another application where a berm would be used, note that there's a very deep failure. The bulge at the toe goes way beyond the original toe of the field. We can get a mass of material at the toe there by extending it and building a berm. A situation where a berm might be used, shown in this failure at a bridge approach. This is a rather large field, and it's one that maintenance probably wouldn't be involved in, but here again they need to be aware of what techniques could be used because they may be inspecting that later on after the repair is made. This is a very classic example where it's a very deep rotational failure where a berm is very effective. You note on your monitor there to the right, we've got a drainage area. Usually it's very soft soils. You can use a berm and flatten the slope to the left there, and this is a very effective technique in these deep rotational type failures. Like I said, when the berm or when the height of the failure gets up over about 30 feet or so, a good combination is go to a flattened slope at the top and build a small berm at the bottom. What I'm showing there, I'm showing safety factors. For just the flattened slope, you get 1.2, and for the flattened slope with the berm, you get 1.5. The emphasis here is not the numbers necessarily. That's what a geotechnical engineer looks at. But for a maintenance person, what I want to point out is that you increase the stability tremendously when you build the berm with the flattened slope. So those are two good combinations. Just an example of use of a berm. Here again, this is a rather large failure that's been corrected using berm. Note that the slope, I think, on the upper part there near the highway has been flattened, probably to about a 3-to-1. Again, another technique, it has a similar flavor as to the berm, is to use a stabilizing keyway. In other words, we excavate down and trench into to bedrock and put in a high-type material, stone or whatever. Here's an example of the use of a berm on a highway. What I show this slide for is that there was a drainage ditch there, and they had to put a pipe under it, but they still managed to put the berm in. Now, I'd like to talk about a case history here for the next few slides where the berm didn't work. One reason it didn't work was because the geotechnical engineers were told not to make an investigation. They wanted a quick solution, and so they did the best they could. Normally, this is about a 25 or 30-foot failure. It's been there for maybe 15 or 20 years. I drive this route myself over the past few years, and I've seen the crack in the pavement for many, many years. Finally, it moved quite a bit, and something had to be done, but the people that wanted it done didn't want to spend the money and go in to make an investigation. But this is a case where the berm didn't work. For one reason, there was a lot of water in this particular field near the toe. Another reason was that the berm was placed on the left side. It added driving force to the failure. That's just another shot of the toe. You can sort of see a hump in the toe there where apparently the failure plane or the toe is humping up. It's failing. Just a shot of the surface there shows the crack in it, and it's dropped down somewhat. So this slide was corrected, and the reason I want to show this is another technique that you can correct a landslide, and it doesn't matter whether it's a big slide or a small slide. The technique's the same. This is a shear trench. This slide was corrected using a shear trench, and let's look at something, look at the principles there. What we're doing when we build a shear trench, we increase the shear resistance. Also, if we build a shear trench in a certain way, we can provide subsurface drainage. Look at the concept here. Basically, what we're doing is excavating the bad material out down to bedrock when we can, and backfilling with hard rock or high-strength stone, basically, such as sandstone or sandstone. Sandstone or limestone. And if you'll note the failure surface there, what we're trying to do is force it through that trench, through the high-strength material. And if we put it into rock, that's the only way it's going to fail. It has to go through that trench. But we've got strong material in there, so we've increased the safety factor. One good place for using a shear trench is when you've got right-of-way problems. In this particular case history we're talking about, just down from the toe of it, there was a right-of-way fence. So in order to not have to go out and buy new right-of-way, the geotechnical engineers decided to use the shear trench technique. When you use shear trenches, you need to extend, of course, the full length of the failure. It needs to be keyed into rock. But let me make one comment about that. Keying it into rock is always desirable, but sometimes you can if you get it deep enough, you can force that failure plane deep and long. And when you do that, you increase the stability or you increase the safety factor. And of course, the third thing there is that you've got to backfill it with good stone. And usually, good stone might be defined as 5%, less than 5% passing the number 200 sieve. Essentially, there's very little fine-grained material in the stone. Number 57s or something like that. When we start building the trench, we need to compact the backfill or the stone. You can compact it with a crawler tractor in place. I would recommend somewhere around 2-foot lifts. Each lift should be 2 foot and compacted. You can usually build the back slopes of a trench, one horizontal to one vertical, or one horizontal to 1.5 vertical. Again, another technique, as I was talking about earlier there, using the berm and a stabilizing keyway, you can just simply build a trench, a small trench where if bedrock is close to the surface, key it in, and you can see that we're forcing the failure surface, we're trying to force it through that keyway, and that increases the stability when we use high-strength material. Let's go back to the case history now. Just another view of the failure of the surface. That shows that it's dropped down, the pavement there has dropped down. We're looking at the shoulder part of the failure. Another view there, you can see it's really moving. So what the engineers did there, they came back in and they already had the berm stone in place, which didn't work, so they just simply stockpiled it very close to where the failure was. So they removed the material, they went down and started building the shear trench. Used a backhoe to excavate it down several feet. Just another view of the back slopes that we talked about that you can build on 1, 1.5, 1 slopes. Another view of the back slope. Now, what they did, and this is highly recommended, they came back in and put geotextile filter fabric against the soil slope. These were very fat clays. The reason they did that is that they don't want the subsurface water seeping in through the clay soil into the stone and clogging it, because it'll wash the clay material into the stone and will defeat the purpose of drainage there. Then they backfilled it with stone, which is shown in this shot here. Notice also they did one other technique. They used a slotted pipe, which they wrapped around the trench. Just another view of the compaction process, spreading the material out. Now, here they've constructed the shear trench. They constructed in segments of about 50 to 100 feet. What they do there, they excavated part of the trench and they immediately backfilled it, because you got to be cautious about building a shear trench because you're excavating at the toe of the slide and you could only make matters worse. But if you have your material handy, you can excavate a section, put it back, excavate a section, put it back. So that's the concept there. Another view of the slide and the finished product. What we ended up here with is 3 things. Flattened slope, which is shown at the top, which is about a 3-to-1 slope. We've got a berm now in place, and below that berm, we've got a shear trench. And I think they got by without having to buy additional right-of-way. It was a very nice repair job. But I also might mention that the second time around, they did the instrumentation and did the necessary footwork and subsurface investigation and installed some sophisticated instruments in this particular slide. But I'd like to emphasize that this technique, even though it was used on a parkway system, could be used on small slides.
One word of caution, Tom.
Yes.
When you use a geotextile fabric, you want to be sure you use the correct one. There are different types obviously for different situations, so you could do yourself harm. Absolutely. If you just start placing the fabric in and not know too much about it. So you want to get some advice on the type of fabric that you need for the situation that you have.
That's an excellent point, Henry. I think the state has standards, different types. They've written up some specifications for that. And it's always good to check with the state staff or a geotechnical consultant. If you're a county or city and you don't have access to the state people, talk to a geotechnical engineer. And I'm going to say this several times because I've seen too many problems where people try to do things and they needed to talk to someone who is trained in landslide control and landslide mechanics. That's an excellent point.
Before you go on, Tom, I've got a couple of comments I'd like to go further. Number one, I'd like to talk for a second about berms.
Yes.
You've been talking about them made of rock, and I think that's an excellent idea. One of the reasons we use rock is that the berm will drain, and when the berm drains, that prevents the water table building up and prevents the effective weight of the berm from decreasing. Also prevents slope stability problems of the berm. When you can't use rock, I think it's important that the maintenance people understand that they must grade the surface of the berm to drain water away.
Excellent
So that
point.
water does not pond. Too often there's a tendency to put a reverse grade and think that they're going to channel the water away on the interface between the embankment and the berm. That's wrong. Also, I think you have to consider whether or not you're going to compact the berm. I think that has to be clearly understood before people go out and start putting berm material in, because that, again, influences the weight. Secondly, getting back to the shear key business, I think we need to emphasize very strongly here the location of the shear key. Maintenance people can't think that we can go just to the toe of the fill and dig out at the toe and put rock in up to the ground surface and correct slides, because the strength of the key really depends upon the amount of weight above the key.
Yes. Good
Going
point.
to the toe and digging out will really not do too much.
Well, that's the reason I showed the
Yeah,
example
and
where we
good
we
example
used
with the
berm with material on the top of it, and that adds a lot of mass or weight over the shear key. So that's a good point. Excellent point there.
You need something to increase the amount of weight on the shear key to give it strength.
That's one reason I'm going in this scenario, starting with one and going to the other. It's a very logical sequence, I think. And those are excellent points.
Quite frankly, when you go to dig out the key, I think the field people find out there's not much sense to designing a key that's any narrower than one dozer blade, because that's normally what you're going to be digging it out with.
Yeah.
I mean, you don't design a 2 or 3 foot key.
Yeah. But I think even though we've used a case history here where it's done on, say, a medium-type slide, these same principles, though, apply to any type of landslide, basically. So that's the emphasis I want to give here on these techniques. But let's go on with another case history. When you're doing shear trench construction, it's very critical in that you're digging near the toe of the fill, and you may have the whole thing to come down on you. So there's some guidelines here. First, construct it during the dry season of the year. When the water tables are low, there's not much surface water running into the slide area. And it's good to construct it, as I want to emphasize this again, in short segments. And as soon as you construct a short segment, you take it out, excavate the material, backfill the rock, put the rock back in quickly, as fast as you can. In other words, if you have to have 4 tandem trucks parked there with stone waiting to place the material, do it. So I'd like to emphasize the last point there, backfill immediately. Let's look at a case history where there was a problem. Shear trench was a solution. What you're seeing there is about, I guess, 12 feet of asphalt. A situation like this, and this is one of the purposes of this course, don't start patching a landslide and adding this much material. If you've passed over 2 or 3 times, and I want to emphasize this, you've got a problem most likely, and either you need to start looking for the causes, and that's the reason we had a session on causes. You're adding weight there. Generally, asphalt weighs about 145 pounds per cubic foot, and soils that are used in the embankments around 100 to 130 pounds per cubic foot. And you're putting on top there this heavy material, and it's on the driving side, so it's simply going to rotate or slide along a wedge-type failure, and you're making matters worse. One thing I said before, if you're going to add that much asphalt, and I don't mean this in a derogatory sense to maintenance or anything, put it at the toe of the field. This sounds ridiculous, but I say that in jest. But what I want to emphasize here is contact someone. If it's a big slide and you're patching the thing 3 or 4 times, call somebody. Call the geotechnical engineer or notify the maintenance engineer that we think we've got a problem. And don't be afraid, if you're a maintenance supervisor, to tell someone. Because a lot of times, if you can get in early on a landslide, you can do things that will save money. But let's go on. This is a case where they did do a shear trench. They built their back slopes, excavated the trench, but a problem developed. The contractor that was doing the job only had 2 trucks running 15 miles to bring the stone in. So we had this open excavation, rather steep there, that began to slough off, and then it started going, the failure started extending to the other side. Fortunately, they got to the problem soon enough, and here you can see some more sloughing off of the back wall there. They did get back and backfill the material. Eventually, they speeded things up. The geotechnical engineers did, and they got the thing repaired. But what I want to emphasize there is that when you do a shear trench, construct it in segments and backfill immediately. If you have to work 24 hours a day to keep the stone there, keep it there and backfilled. Another technique that's used is benching, and I'm not going to go into too much detail here. There's things in the book you can read. Benching is used in situations where we can't, this is in a cut slope, where you can't do a lot of slope flattening, and you simply bench the slope to try to stabilize a particular condition. Benching is used here perhaps to catch material on the slope. The main reason I show this slide in certain cases where benching is used in certain localities of the country, maintenance may be involved in cleaning off those slopes. So you should be aware of the technique and what role you may play in it. Of course, Dave talked about benching for new construction and so on, and I won't say too much about that. Just some overall considerations when you flatten the slope or build a berm or bench or construct shear trenches. There's perhaps some things we need to be aware of. First of all, we need to be aware of right-of-way. Where is the right-of-way? And this is where sometimes the inventory system can be very handy, because before these landslides developed, say, for example, that you've got, it's showing some distress signs. Here's where some pre-planning might come into play. When you're doing your inventory system, you've got a possible slide out there. One thing you may do is find out where the right-of-way is, because you may have to use slope flattening or a berm or so on. If you've got enough room, you may not have to worry about things, but you need to know where the location of that right-of-way is at a particular slide. And you can either go to the courthouse or during the spare time. I doubt if maintenance has too much spare time, though, but you can do a little footwork in advance if a section's showing distress. Of course, you've got to be aware of the topography of the site. Can you move heavy equipment to the toe to do the work? Do you have access? Here again, the inventory system would be very valuable, I think, that if you've got a section of highway that looks like it could fail, sort of think out these things. Think out, how am I going to get equipment to the toe if I've used slope flattening or berm or some technique? How am I going to do this? And you could put this in your notes where you've inventoried a particular section. Just a place where it might be difficult to get down to the toe of the field, so you need to take a look at that. Another thing, when you're doing the inventory system, availability of suitable borrow. If you've got sections of highway that are showing distress, you could pre-plan and say, well, if this thing fails, I may be able to get material out of this cut section here. Maybe I can handle two problems at one time. I'll flatten the slope on the cut. I've had rocks dropping on there, and I'll take that material, which is just a few feet away, and I'll build a shear trench or some type of berm there and correct this problem. So the main emphasis here is to try to do some pre-planning. The inventory system would kind of be the type of thing that could help you pre-plan. Also, of course, we've got to be aware of the availability of the personnel and equipment and so on, and constraints. Obviously, maintenance is always strapped for money. Don't try to go out and spend $300,000 on a landslide when maybe your budget's only $2 million. Okay, that concludes some of the techniques on slope flattening and so on, the first part, modifying the slope. Now let's talk about subsurface waters, control of subsurface waters. Dave talked about controlling surface water and went into some detail and the things we can do earlier in this workshop. I'm going to skip over a few pages there in your manual and go right on into the subsurface waters. think that may be, we'll start on page, let's see, page 128 in your manual. Here are some things that you can do for controlling subsurface waters. Maintenance may or may not be involved in these techniques, but you need to be aware of these techniques, and I want to point out some things. The reason I'm going into this is that you need to understand some of the concepts, and I want to point out some of the things that maintenance may be involved in when these are done. A lot of times some of these techniques may be done or performed by a geotechnical engineer, and which is let to contract, but there's things that maintenance needs to do to follow up. First of all, horizontal drains is one technique, drainage blankets, cutoff walls, vertical well points, and seepage tunnels. And vertical well points also includes vertical well drains. Let's look at horizontal drains first. This is oftentimes a very good early treatment method for side hill fields. What we're trying to do in using the horizontal drains, we're lowering the water table or the groundwater table in the slide material. Applications not only to treating side hill fields, but it's good application for deep failures. And failures where the embankment's been placed against pervious water-bearing strata. Let's look at the concept a little bit more here. Basically what we're doing is putting in or installing horizontal pipe in a drill hole, and we're trying to intercept the water table, which is shown to the left of the monitor there, trying to intercept the water before it gets into the landslide or gets into the embankment. This is a view of the type of drilling equipment that's used for installing horizontal drains. What they do there, they use case the hole. It's a special type of drill in that it can drill horizontally instead of vertically. And then they drill back and case the hole, and then they insert a slotted plastic pipe into the hole. These are the steps involved, and generally the drilling is done on a grade about 3 to 20% so that we get gravity drainage. And the diameter of the slotted pipe is usually around 1.5 to 2 inches. They use a special type disposable drill bit. In other words, the bit's mounted on the horizontal casing on the end, and they drill the casing back in. They don't want to lose the casing, but they have come up with a disposable drill bit, so they just leave it in place. They just backspin the casing and pull the casing out. Well, first, before they pull the casing out, they insert the plastic pipe, the slotted pipe. Now, the pipe is either slotted or perforated. Generally, what's being used today when you're installing horizontal drains is a plastic type slotted pipe. And for different types of soils, the slots have different widths and so on. I guess California sort of pioneered horizontal drains. They've got so many problems and so many landslides there. They sort of pioneered those type of this technique. And originally they used metal pipe. So they have a lot of old installations there that have been in for several years and have worked very effectively. Generally in the installation of horizontal drains, we're installing them, as I showed in the previous diagram, in the lower portion of the slope or below the toe of the slope in the natural ground. Generally the patterns of installation, well, they're installed in rolls and fan shape. And this is the installation showing where they've installed several rolls of horizontal drains. Here's another close-up of installing in a fan pattern. Visualize in that particular diagram the drains and the casing running in all directions there. Some important things about the installation. Generally the spacing when they're in rolls are usually about 30 feet or less. To prevent clogging, they do two things. They wrap it with a sort of a filter fabric cloth or sock, if you will. That's what the slotted pipes wrap with, although some specialty contractors say that they don't do that. but that's a matter of choice, I suppose. The last thing there, they leave the last 20 feet, the part that's coming out of the ground, they leave it unslotted. The reason for that, they don't want the roots to grow into the pipe. If you remember, earlier Dave showed a pipe section where the roots were growing into it. Well, it's sort of the same concept. They don't want the roots to clog up the end of the pipe. Now, the part that maintenance should play in horizontal drains. First, we've talked about the concepts here. They should understand a little bit about what's involved here, but maintenance can play an important part. Maintenance should monitor the discharge on these pipes, and they also should flag these locations after they're installed, and they should keep them clean. Here's an example of an installation. They spent a lot of money putting these horizontal drains in. They're clogged up. They need to be unclogged. So a good policy for maintenance to do is to, if they have a site where they're installed, is to put it in the inventory where that installation was, the location, the milepost, or whatever, and keep the ends of the thing clean so that the drains have an opportunity to drain. Do they work? Well, I think this slide illustrates it very well. Generally, when you first put these horizontal drains in, they'll drain quite a bit. And then they may stop. Well, the reason for that is they probably were very effective. You've lowered the water table in the slide, and they may stop. Then it may be go through a winter or something, and all at once you may go out there one day and see them draining again. So if you're doing an inspection, if you see no drainage, make a note of it. Or if you're out there and you see a drainage, get a bucket and measure the discharge so that you'll have a record of how well that's performing. Another thing, when you install horizontal drains, you always need to do some footwork. You need to define the embankment conditions, the foundation conditions, and the groundwater table. These things are essential. And it's always good to install, as Dave talked about, piezometers or case water observation wells. Well, maintenance will not be doing this function of the subsurface investigation, so on, to decide whether the drains need to be installed, but they play an important role in keeping things clean, and they could also, most installations, you would have a piezometer or an observation well in. Maintenance could read that and keep the data on it and keep in touch with the geotechnical staff in the state. Let's talk about a third method of controlling subsurface waters, drainage blanket. I think at this point we're going to take a break here. Okay, we're talking about subsurface waters and the control of subsurface waters. Another technique, and I'm going to emphasize this in the course, is using drainage blanket. This technique is used with a lot of the other repair methods, or in combination with the other repair methods, such as slope flattening and berms and so on. Let's take a look at some different situations here. We showed this earlier in the session. What we're basically trying to do is put a draining material back in against the excavated slope. We're trying to control the groundwater. In other words, we want to keep that groundwater out of the new field, because if the water gets into the new field, then it's going to lower the strength and lower stability. Another situation where it's good to use a drainage blanket is under the backfill or behind retaining walls. Again, we wrap the stone with a geotextile. Again, we're trying to keep the water table back out of the backfill or behind the retaining wall. Now, there's another technique that Dave mentioned earlier is using a vertical type plastic drain, which is placed directly on the back of the wall. That is a good technique, but this is just as good here where you can slope the material back, because we're getting more water. We're keeping it to the right there. We're keeping it back out completely of the backfill material. So we're gaining a lot more stability in this case. Another scenario, we talked about slope flattening and berms, putting drainage blankets, and also I might mention in all these techniques, it's good to use a collector pipe. And then of course you need to slope the collector pipe or system to where it's draining, where you can get gravity drainage. Under replacement fill, again, maybe a little bench in there, as shown at the bottom, and use a drainage blanket. Run it up on the slope part of the way so that you can intercept any water coming from the groundwater surface there. Also, if you're placing that blanket against, or the stone blanket against a clay or silty type material that has a lot of fine materials in it, here again you want to wrap it with a geotextile so that we can prevent the stone from clogging up. A good application here at the toe of the slope is use sort of a toe drain. In other words, excavate a little bit of the toe, use some geotextile and good stone, wrap it, and you can really lower the water table quite a bit there and increase the stability tremendously. I'd like to make one point about embankments, and I may have said it earlier. The toe is the most important part of that embankment. Protect the toe of that embankment at all costs if you can, because that's where, in geotechnical terms, where there's a high concentration of stresses, and if you do anything to disturb that toe, such as removing the toe material or getting it saturated, you really decrease the stability of the slope. Just an example application where the drainage blanket was used. This is a slide where maintenance had put in several feet of asphalt to try to keep the road open. Here again, I'd like to emphasize, don't let a situation get this far before you call the geotechnical staff or start looking for the causes of the slide, because when you get this type of vertical movement at the top of the slope, you've got a landslide, quite obviously. And here again, if you add material to it, you're increasing the driving forces. But this slide doesn't show up too well, but the black material there is a stone and the white is a geotextile. They're installing the drainage blanket. Completed view of the site, you notice that the slope's been flattened, and this is a very good repair job. Another technique that's been used, or at least attempted over the years, is using a drainage trench. In other words, we come in with a backhoe on the upslope of the embankment, dig a trench and backfill with stone, maybe use geotextiles. The problem with this is that we may not intercept the water table, and the drainage trench is very ineffective. If you're going to do this sort of thing, put the drainage trench down at the toe of the embankment, because we'll have a better opportunity at least lowering the water table some. Okay, another method of controlling subsurface water, vertical drain wells. Basically, this is a concept of drilling a hole in the upslope where that trench was. Instead of using the trench, we're drilling a hole we're backfilling with gravel or sand. What we're trying to do there is to intercept the water table. Generally, the vertical drain wells can be more effective because we can go deeper and we can have a better chance of intercepting the subsurface water or groundwater table. And we can, vertical drain wells can be either pumped or not pumped. When they're pumped, they're just a temporary control because it's very expensive to go in and try to pump the water out from the vertical drain well. Also, we can take a vertical drain well and join it with a horizontal drain. As we talked earlier about horizontal drains, we were drilling back from the lower portion of the slope, and we can drill back and connect to the vertical drain. Now, these are not techniques that probably maintenance will get involved in, but they should be aware of what the concepts are, because there may be some maintenance follow-up on, say, geotechnical people may have done a job like this, and maintenance needs to follow up to see how well these things are working. When well points are just generally used for temporary control. For example, if you were building a shear trench where you've got a high water table, well points might be installed around the site to lower the water table until the trench is backfilled. Just some guidelines on well points. These are outlined in the manual. I won't go into it too much more. Vertical drain wells, well points, like I say, well points are generally used for repairs or new construction. Let's just take a look at how these vertical wells might be installed. They use a special drilling apparatus, or one that's used for drilling caissons. The diameter of the auger there is about 2 or 3 feet, and they simply drill a hole in the ground, and they use, when they get down to a certain depth, they use what they call a belling tool. This thing device has arms that swing out when they, in other words, they drill down, and at the bottom of the hole, the arms start swinging out, and they bell the bottom. They cut a bell-shaped groove. Then once they do that, they backfill with sand or gravel. And like I say, a technique that has been used is to take the vertical drain wells and join them with the horizontal drains. Now, there's some criteria outlined in the book for this sort of thing, and I don't think I'll go into this in too much detail. Let's just go on here. What I wanted to show here in this slide was that you could connect up the bell bottoms of the vertical drain in certain situations, and perhaps use gravity drainage. Or you can, in certain situations, you may have to try to drill back into and connect up a horizontal drain with the vertical drain. Seepage tunnels is another technique that's used to control subsurface water. This is an extremely expensive method, and maintenance won't be involved in this. In fact, very few people are involved in this type of technique, so it's not really that important to us. Let's turn our attention now to retaining structures. Retaining structures are used quite often in highway repairs. What we're basically doing is putting a mass of material or a wall at the toe, perhaps, of the slide. But let me emphasize, this is a very expensive solution, and you should look at the other methods first before you consider a retaining structure. Oftentimes, it's misused, and we'll talk about that just in a minute. Let's look at some of the basic types of retaining structures that can be used. There are situations where we may have to use a retaining structure, but we should be able to identify those situations. Some of the retaining structures that can be used are concrete walls, earth and rock buttresses, crib walls, gabion walls, piles and caissons, tied-back walls, tide piles, reinforced slopes. Now, what I'd like to do is go into a little discussion of each of these methods. What I'd like to emphasize is that you have to be careful in using the retaining wall at the toe of the field, because in this case here, the failure mass, which are the 3 dashed lines there, is much greater than the ability or the soil wedge behind the wall, or that wedge is what the wall can retain, but our failure mass is much larger. So what happens in situations like this, and we've got to be cautious when we use a retaining wall, is that it may the shear surface or the failure plane may undercut the bottom of the retaining wall, or if it's a very large mass, it simply shears through or just pushes it over. So those are some things that you need to be concerned about. Generally, as just a rough guideline, the soil wedge supported by the wall, that's sort of a theoretical wedge, should be about the same size as what your failure mass is. Here again, let me emphasize that when you're doing your inventory, you can kind of, if the thing has moved enough where you've got a scarp and a scarp at the top and a toe bulge, there's a technique in the manual there for approximating what the failure mass looks like, what the shape of it is. And during your inventory, if you've got just a cross section, you can get an idea of what that failure mass looks like from the technique in the manual, and compare it to the guidelines that I show here. In other words, that slope there, 1/8 to 1 horizontal to 1 vertical to 2 vertical, you can plot that line, and that's about what that retaining wall is going to retain. It can't retain much more than that. If we increase the depth of the retaining wall, as shown here, we can make our theoretical or what that wall can retain, the mass that it can retain, we can make it a little bit larger, and we can go, some systems or the retaining walls use this concept, or a lot of them do. Applications, we can use it in small slides in certain instances, slides with steep toe slopes. We've got to be cautious, like I said earlier there in the diagram, where the backward extension of the failure mass into a larger mass is not likely. We can use it for supporting flattening, slope flattening, and berm. Some cases where the berm comes out, you may have a right-of-way problem, so you may stick a retaining wall right at the end. You still not in danger, maybe in certain situations, of the thing felling, but you don't have to go out and buy additional right-of-way, as the last point there. In this case here, this is where we've used slope flattening and the berm, and we had a right-of-way problem on the right of the wall there, so we stick a wall out there, a small retaining structure. But note that our slide plane is back away from the wall, so you can use you could get by in this situation with using the retaining wall. Now, there are certain situations, though, where a retaining wall may be the only practical solution. For example, long, shallow failures. Now, if we try to flatten the slope on that, what's going to happen? We're going to go forever, because the slope below the toe, the natural ground slope below the toe of the berm, the field, the failing mass, is very steep, and it just continues on downhill. So here's what we could do in a case like this. We could use a retaining wall, and note that we've only got a small mass of material on the upside of the slope there to retain. So retaining walls do have applications. They, like I say, they're misused, and they're very expensive to build. So, but some cases we have to use them. Concrete walls, that's another method that's used. They have somewhat of a limited use in highways to some extent, because generally retaining walls is a very rigid structure. It requires a rigid foundation. And the main thing is it cannot tolerate large settlement, and it's also rather expensive. There's different types of retaining walls, gravity types, semi-gravity, cantilever, and counterforce. Those are explained in the manual, and I won't go into detail here because I don't think it's important at this point. You can read them in the manual. But I do want to talk about a case history now where concrete can be very effective. This is a situation in one of the counties, local counties in the eastern part of the state. This is where an inventory system was used extremely well. This particular county official had many problems like this. And let me explain what you see and you're looking at there. You've got a small stream that's eroding or undercutting the toe, and we showed this earlier in the presentation. And what you've got there, you get little sloughs or wedge-type failures into the stream. And this particular local official had he's got hundreds of these kind of problems. So and he surveyed his problems, I think. He realized how am I going to fix this? Well, he used a concrete barrier wall, or a portable wall, actually. And this is a very nice scheme of what he did. He got with a local concrete company, and they made a special form to make a concrete wall. But it's a portable unit. What you're looking at there, that's after they cast the material, the concrete. As I showed in the previous slide, he uses a little reinforcing steel in there. And he stockpiles these small walls in the concrete yard and goes and gets them when he needs them. Now, let me explain something about the little wall units. They're 8 feet long, so they fit in a dump truck. They're about 1 foot at the base, about 6 inches at the top there. And note at the top of each one, they've got a little hook. And what that's for, he can lift that with a backhoe and place it in a dump truck. It's short enough, it'll fit. And this shows the placement of the wall. Now, these people can, this particular maintenance crew can go out there and repair a small slip like this in 3 or 4 or 5 hours. And that shows the placement. And what they do, they excavate a little part of the slide area out, place the wall in, and here's a little bit more construction detail. You notice there's 2 hooks on each adjacent wall there. Now, when they precast these, they leave some reinforcing steel hanging out at each end. And what they do, they bend one end over and fit it through the hook, and bend the other one, the adjacent reinforcing steel, and bend it through and put it through the hook of the other. So he ties the walls together. I think it's kind of a neat design. And like I say, he can place these very quickly. Here's another detail or a close-up of the locking mechanism that he came up with. Just another placement, showing placement of the sections using just equipment on hand. It's not very sophisticated backfill, but it works. He just scoops it out of the river and backfills. And he backfills it about to a third. And then he uses an anchor block, which are precast and stored at the concrete company's a concrete yard. And he connects the anchor to the wall at about a third, and then he ties the steel coming out of the wall with the anchor block. And then he backfills on up using what's available there. Well, I asked him, this is not very sophisticated in a way, but it is a neat little system because it solved a lot of his problems up there, and he's had these in for, he's been doing this for about 5 years. And they work quite well to solve his particular class of landslide problems. I asked him, does he have failures? And he says, I do. He says, all I do is go out, and he leaves that hook at the top of the wall. He simply pulls it back in place. If it falls over, he pulls it back and takes his backhoe and backfills it again. He's solved his problem. And like I say, a 3 or 4 man crew can go out and solve a 8 or 4 to 5 foot landslide problem in 3 or 4 hours. So this is just one way. If you know what your problems are and know what type of landslides you're encountering, you can pre-engineer some solutions. Incidentally, this particular official was an engineer, a graduate of the University of Kentucky, who is now the county judge executive there. But he is pre-engineered. He's taken stock of the kind of problems he has, and that's what I want to illustrate here. He's come up with a solution to it. Now, maybe you're not an engineer as a maintenance supervisor, but you can get with an engineer who could look at your problems. If you've done your footwork and got your inventory, a geotechnical engineer could take a sort of an overall view of what type of slides you're having in your particular locality and maybe devise a system like that. And that's the reason I wanted to show this case history. Just another view. These walls, I should have mentioned, are about 4 feet tall, but he can stack the walls, I think. He has stacked them too high, or he can come in and put a gabion wall, which we'll talk about a little bit later, put it on top there. But he's solved a very difficult problem there. And I've been up in that county on occasions during flooding, and he has hundreds of these type of problems. Okay, the same thing can be done with old safety barrier walls. You can build the same type of structure. One thing I might mention that he did that you ought to consider when you're using a safety barrier is try to anchor the top of try to anchor the wall with an anchor block, just like he did. Here's one application of a safety barrier wall, which works very well. There are engineered type walls this is one that's called a double wall. Actually, the trade name doesn't have the last L on it, but I put the last L in. And what these are precast modular units. They're hollow inside. Just another view. They come in different sizes. If you could look over and look down in the thing, it's completely hollow. It's called a double wall. There's 2 walls there, front and back. And they can be stacked in various patterns. They come in various shapes. For small slides, probably less than 20 feet in height, you could probably get by with maybe an 8 or 10 foot section there of this type wall. Notice that it's stacked. You can batter it. And what you don't see here is that you have to pour a couple of little concrete footings for this type of wall, or it's good to do that. One in the front and the heel or the back side, the right side, you pour another concrete footing. But these can be brought in. They're usually brought in by a lowboy or a truck. There's a special device they use for lifting those out. These are lifted out by crane. But you can build these walls rather fast, though. They are expensive, like most concrete walls are, but This is just another technique that can be used for correcting landslides. Here's another view of placement of the backfill in there. Notice that they've got if you look in the lower right-hand part of the screen there, that's sort of a hand compactor. They're compacting the material, and generally they're compacting about 4-foot lifts. But this is a pretty fast system that can be installed rather fast. Earth and rock buttresses. Let's turn our attention to another technique. Some of the things about an earth and a rock buttress. This can be used to repair several different types of landslides, and it is used or has been used. This technique can be used very effectively in small landslide repair. Generally, the buttress volume has got to be about quarter or half the failure volume. It needs to be keyed into rock. It's best to use rock fill for the buttress. Generally, there's some other guidelines there for rock slope. You can almost go up to 1 horizontal, 1 vertical. This is a big landslide where they use a rock buttress down in Tennessee. The rock buttress is on the right of the screen there. And they also combine that with horizontal drains to control a massive landslide failure. But we can use a rock buttress for small slides. For example, a typical situation that occasionally occurs over a box culvert where the water runs down from the surface or groundwater gets in and causes the toe of the slope to be saturated, and what you end up with is a small toe slump, as shown here. What we can do is come in, excavate the material out, and simply replace the excavated material with rock, a good stone. It sort of shores up, or it's a buttress for the rest of the slope. Obviously, here again, you need to work real fast if you're excavating the toe of the slope out. Don't waste any time. Don't go smoke cigarettes or that sort of thing, but pay attention to getting that backfill in as fast as you can. Now, in certain situations like this, you may have to have some kind of a clamshell or something to remove the material. But it illustrates an important principle. Now, what we would recommend here when you're installing that is to use, if you're going to be placing the stone against the clay slopes or silts, use the geotextiles to protect the stone. And another good policy is use some kind of a flexible slotted pipe that you could curl around at the bottom of the buttress. Another example where a buttress could be used, here again this particular slide looks like it's a shallow failure because the upper scarp there, if you notice, is sloping quite a bit. It looks like sort of like a mud flow, which you could come in and excavate part of that out and replace it with rock. Here again, you're going to place the rock against a geotextile, which was placed against the excavated slope. Just another view of that of another type of slide where you could use this is shown here. You notice that in the lower left part of the monitor, you have a toe slump. You could simply remove that material and replace it with rock, as shown here. Here again, you're using a good strong stone with almost no fines in it, putting in some type of slotted pipe, and you may have to run an unslotted pipe from that point on out to get the water and keep the stone drained. And that can be very effective in repairing small landslides. Same thing can be applied where you have a small slump at the top of the field. Again, use the same technique. Let's talk about briefly some other...
Before we go on,
Sure.
One comment about that blanket of stone that you showed, particularly for the mud flow type slides. If we're going to be constructing blankets that are 2 to 3 feet thick coming down the slope in mud flows, they need to be keyed in at the toe.
Yes.
Most of them cannot support their own weight.
Mm-hmm.
So you're going to have probably whatever the width is of the blanket, the thickness of the blanket, at least that much embedded below the ditch line itself.
Mm-hmm. That's a good point.
The second point I wanted to make about these is that these toe slumps, once you put in your key first at the toe, then you should put your filter fabric in, as you mentioned, and you should not place the stone with a bucket at the top and let it roll down. You should preferably take a dozer and start pushing it up the slope so that you have a chance to key the stone in and have a good, firm, compacted area over the filter material when you get through.
That's excellent points. Very good points to make here. And okay, to continue, let's talk about some other type of wall systems, crib walls. Crib walls can be used in small slides up to about 20 feet. It's used in situations where you've got undercutting of the toe of the slope, and there's certain advantages using a crib wall if you're comparing it to a concrete, or which is a more rigid wall. The crib walls will usually withstand a lot more movement than, say, a rigid wall. Basic components, simply you have either concrete beams that are notched and placed in that fashion as you're looking at, and it's backfilled with some type of granular material. Here again, notice that we're developing depth of the wall, which we're increasing the wedge that we can retain. We're making it larger than just, say, a thin wall. Just a view of a crib wall in place, used here on this particular highway at the toe. Another system is called crib block. Notice that this is 3 sails, and notice the depth of that wall. You can vary that. Another view of that particular type of crib wall. The reason I want to show crib walls, those are fairly expensive solutions to a landslide, but here's a cheap solution that may or may not work, but that worked in this case. In this same county that I was talking about, they had some discarded timber or cross ties from one of the coal companies there, and they made a crib wall. And what they did, you can't see the depth there, but those circular faces there go a few feet back. They're square, probably on the order of 5 or 6 feet square there. And he took those discarded materials, which were given to him. It didn't cost him anything except to haul them out there, and he made him a crib wall to solve the landslide problem there. And he used large spikes to drive those particular materials together. You could do the same thing with notching and building something, a very similar thing like a log cabin or something, and then backfilling with whatever material he had in place there. In this particular county, the materials are sort of silty and sandy, so he can backfill with what material is available. Here again, recognizing the kind of materials that are available in your locality is a pretty important thing. You can use very cheap materials if you've got the right type in a particular locality. Another view of a retaining wall, looks like you're using something like just logs there and some lumber on top. Same concept of a crib wall, interlocking or notched out members, sort of like a log cabin effect there. But he's using the same concept of the engineered crib walls, and it's worked very well. In your manual, there's some guidelines outlined for building crib walls. I might just mention a few of these because I think they're important. When the height's greater than 12 feet, you need to batter the wall to what's shown there. You need to bury about 10 to 20% of the wall below grade, and it's preferable to use a granular backfill. That's good. The rest of the details are in the manual. Here's another technique that's used, gabion walls. This type of system is used for controlling erosion around streams. It can be used as part of a berm or a flattened slope, especially where the berm or flattened slope maybe comes out close to the stream bed. Generally, these walls are fairly economical, up to about 20 feet. One particular application, as you see here, is you have a situation where you have a stream bed, a stream that's cutting or undercutting the toe of the slope. It's shown here, and it's eating out the toe, and you've got a failure that develops because of the erosion of the stream. this is a good application of gabions. Here again, you need to use good drainage behind the gabions. Here's another application of gabions, which are, I should have mentioned, are wire baskets that are backfilled with rock. They're generally square. Just another example of where a gabion comes out at the end of a berm near a stream. Components basically is just a wire mesh, baskets, if you will, that's backfilled with stone. Generally the stone that you use in gabions is graded to be about 4 inches to 8 inches in diameter or size. Here again, the features include just interconnected wire mesh containers, as I showed previously. Those are some of the details. You can look at those in the manual. This is what a standard gabion basket looks like. It's got 3 cells there, and you backfill that with rock and close the lid down. They have to be assembled, put together with wire. Just some typical features that are listed in the manual. The containers, usually about a 13 gauge wire is used. Like again, I might say they're backfilled with stone. One application of a special type of gabion where you've got high erosion near the toe of the slope, and even though you're putting a gabion in, it may be desirable sometime to extend the gabion across the stream and up the slope. And they make a special type of gabion for that. They call a mattress gabion. And this can help prevent the erosion. This diagram shows what it looks like. They're about, I think, about 6 inches tall, so they're very thin. Gabions are shipped flat, as shown here, in stacks, and like I say, you have to put them together. They have to be assembled with wire. But the nice thing about a gabion, or one good feature, is that you can make sub-assemblies of these. You can put several of these together. For example, in a maintenance yard, you could store these and make them as large as you can haul out to a particular site, but you could keep them stored there already pre-assembled. So they would have some advantage if you need to grab them and run and try to correct a failure. They can be mechanically filled, but one important thing when they're filled with, say, like this particular situation, you need to lower that bucket down as low as you can and not drop the material down into the gabion, because that'll deform it and cause very bad problems. Also, that you can fill them by hand, which is be quite a bit of work, but I think a lot of them are mechanically filled. You could use other types of equipment to do the backfilling.
Tom, one word too here. Caution, gabion is certainly a good device to use as far as retaining structures, but you want to be aware of the environment. If you're in say in a coal mine area where you're subject to acid runoff, you want to be sure that you've got these adequate protection for the wire. Obviously, with some galvanized wire or something this sort of something to protect it, so you won't have the environment attacked in the wire itself.
I was aware of that problem, and in the manual I mentioned what we call a standard. It's American Society for Testing Materials. I've given a number so that if you were buying these from a vendor, you need to check to see if he complies to that standard, and that's one reason I listed that particular standard.
One of the other things we've done, Tom, we've put these in place to keep them square while we're putting them in. We'll put reinforcing rods in each corner.
Yes.
And then leave those up to the height of the basket.
I'm not
and
mentioning, excuse me.
They don't, that way they're not in the way, and they keep them square if you are, mechanically loading them with, with a small backhoe or something.
I think in the manual, I'm leaving some detail out. It's in the manual for time's sake for this purpose, but there are installation details. One thing I'd like to say about a lot of these different systems that are sold by different or engineered systems, all you got to do is call these people up, and you'll get unbelievable wealth of information. In fact, there are some companies that will even design a particular situation for you. So all you've got to do is find the name of someone that sells gabions or double wall or some of these systems, and you'll get all kinds of information. A lot more information that we could possibly give to you in one day. So if you want design standards, design situations, a lot of these companies have already designed a lot of this for you. So they could tell you, look, if you could tell them something about your site, they could probably send you a design for it. So that's a good source of information, I think. This particular slide just shows the placement of gabions at a particular location. You see they've assembled the things. Like I say, those could have been pre-assembled in small segments and brought out to the site and then put in place. They could be assembled in the maintenance yard. In this particular slide, this is a good application of a gabion. You've got perhaps a stream, or a dry bed stream, you might say, but it's used to protect the toe of a large slope. Very good application. It holds things in place. You also can use gabions, the mattresses, for drainage ditch and controlling surface water runoff. Another good application is at bridge approaches where there's a river. It's not shown here to the right, but they're protecting the toe of the slope with a gabion wall. Those gabions there are probably about 3 feet, I think, in height, so that's about a 9-foot wall there. Also, you can use the same concept to protect the slope and of a highway field here, a small field, perhaps less than 20 feet, but it's doing a good job. One caution about using gabions, though, if you have bad or poor soft clays, you might get a situation like this. Also, notice that, it may be hard to see, but this is bad backfill material. It's got a lot of clay or clay shell material in it. I'd say part of the problem there is a poor foundation, and it simply failed, the foundation did. So if you're in a situation where the ground appears to be soft, you need to call a geotechnical engineer perhaps before you use a gabion wall. In other words, you want to put all these walls on a fairly good foundation, and sometimes it may be necessary to come in and get a geotechnical engineer to do a little study of the site and give you some recommendations on the footings, or not footings, but I mean the foundation conditions. Metal bend wall, that's another cellular type wall, as shown here. It's been used quite often. Now, here's another type of wall. It's just used in culverts, probably 30 inches in diameter, but they're backfilled, stacked and backfilled with gravel or whatever's handy. But it could be a very simple solution to a small landslide using this type of thing. Now, I think California has developed some pre-engineered, you might say, design standards for this. But anyway, that could be a very good solution. Okay, let's turn to another type of system that could be used to repair a small slide, piles and caissons. This has been used quite often in landslides. Basically, the concept here is driving or drilling in piles, within piles may be wood or steel or whatever, and putting the piles in rows. This has been used, and it's a very common practice in highway maintenance, or has been over the past few years. I guess one reason is it's a very quick treatment. It's easy to go out there and drive a pile real fast, or drill a hole and put a pile in it. But I want to mention and caution you on using this type of system. It's frequently misapplied to large slides. It perhaps can be used up to slides up to about 20 feet in height, but when you start getting into much larger landslides, you're going to get into trouble most likely, because you've got to remember that a pile system like this, if it's steel, it's a very flexible, thin diagram that you're trying to hold back maybe a large mass of material. Again, this just shows that the piles or caissons are put in rows, and I might mention, I think we need to define what caissons are. Caissons are drilled in. You come out with a drill and drill a hole and you either put some steel in the hole and backfill with concrete, or it could be just all concrete, or you could use a steel cage and drop it in the hole and then backfill with concrete. This has been used in certain areas of the country, and it can be effective sometimes, but here again, you have to be cautious in using piles to try to correct a landslide. Installation might involve putting a roll of piles at the top of the slope and one near the toe. Now let's look at some failures. No one likes to see a failure of any type, but these are cases where piles were very ineffective. They were driven in. For example, here, and let me point out one thing about this particular slide. You see a sort of a casing, a blue casing sticking up. This is what Dave was talking about earlier, and this is something you should recognize if you're a maintenance person. That's a slope inclinometer, and what that does, that tubing, they have a torpedo that goes down into the tube, and what they use that for is to determine how deep the failure plane is. So if you're a maintenance person, look at that slide very closely, protect that for the geotechnical engineer. He needs that protected. Because he may, that particular type of instrumentation, like Dick had mentioned earlier, may stay in 15 years or more. I have made installations where I've had slope inclinometers at bridge approaches in for some 14 years. And we got a wealth of data from it. Because if you don't hang around to get those kind of slow movements, and these were very, very slow movements, you don't know what's going to happen there. If you measure it just for 1 year, it may show very, very small movement. So I'd like to emphasize to maintenance to protect those type of tubes if you see them sticking out of the ground. But going on with piles, when they're driven in, they fail. There's numerous case histories of pile failures. We could have collected probably 200 cases in this study.